In number theory, the law of quadratic reciprocity is a theorem about modular arithmetic that gives conditions for the solvability of quadratic equations modulo prime numbers. There are a number of equivalent statements of the theorem. One version of the law states that for p and q odd prime numbers, and denoting the Legendre symbol, this law, combined with the properties of the Legendre symbol, means that in any Legendre symbol can be calculated. This makes it possible to determine, for any quadratic equation, where p is an odd prime, if it has a solution. However, it does not provide any help at all for actually finding the solution. The solution can be found using quadratic residues. The theorem was conjectured by Euler and Legendre and first proved by Gauss. He refers to it as the fundamental theorem in the Disquisitiones Arithmetici and his papers. Writing the fundamental theorem must certainly be regarded as one of the most elegant of its type. Privately he referred to it as the golden theorem. He published 6 proofs, and 2 more were found in his posthumous papers. There are now over 200 published proofs. The first section of this article gives a special case of quadratic reciprocity that is representative of the general case. The second section gives the formulations of quadratic reciprocity found by Legendre and Gauss. Motivating example. Consider the polynomial f equals n2 minus 5 and its values for n equals 1, 2, 3, 4. The prime factorizations of these values are given as follows. A striking feature of the data is that, with the exceptions of 2 and 5, the prime numbers that appear as factors are precisely those with final digit 1 or 9. Another way of phrasing this is that the primes p for which there exists an n such that n2, 5 are precisely 2, 5, and those primes p that are 1 or 4. The law of quadratic reciprocity gives a similar characterization of prime divisors of f equals n2 minus c for any integer c. Terminology, data, and 2 statements of the theorem. A quadratic residue is any number congruent to a square. A quadratic non-residue is any number that is not congruent to a square. The adjective quadratic can be dropped if the context makes it clear that it is implied. When working modulo primes, it is usual to treat 0 as a special case. By doing so, the following statements become true. Modulo a prime, there are an equal number of quadratic residues and non-residues. Modulo a prime, the product of 2 quadratic residues is a residue, the product of a residue and a non-residue is a non-residue, and the product of 2 non-residues is a residue. Table of quadratic residues. This table is complete for odd primes less than 50. To check whether a number m is a quadratic residue mod one of these primes p, find a m and 0 are less than p. If a is in row p, then m is a residue. If a is not in row p of the table, then m is a non-residue. The quadratic reciprocity law is the statement that certain patterns found in the table are true in general. In this article, p and q always refer to distinct positive odd prime numbers, plus or minus 1, and the first supplement for all prime numbers, plus 1, is a quadratic residue. First of all, for which prime numbers is minus 1 a quadratic residue? Examining the table, we find minus 1 in rows 5, 13, 17, 29, 37, and 41, but not in rows 3, 7, 11, 19, 23, 31, 43 or 47. Minus 1 4, minus 1 10, etc. The former primes are all 1, and the latter are all 3. This leads to the first supplement to quadratic reciprocity, plus or minus 2, and the second supplement for which prime numbers is 2 a quadratic residue. Examining the table, we find 2 in rows 7, 17, 23, 31, 41, and 47, but not in rows 3, 5, 11, 13, 19, 29, 37, or 43. The former primes are all plus or minus 1, and the latter are all plus or minus 3. This leads to the second supplement to quadratic reciprocity, minus 2 is in rows 3, 11, 17, 19, 41, 43, but not in rows 5, 7, 13, 23, 29, 31, 37, or 47. The former are 1 or 3, and the latter are 5 or 7. Plus or minus 3. 3 is in rows 11, 13, 23, 37, and 47, but not in rows 5, 7, 17, 19, 29, 31, 41, or 43. The former are plus or minus 1 and the latter are all plus or minus 5. Minus 3 is in rows 7, 13, 19, 31, 37, and 43 but not in rows 5, 11, 17, 23, 29, 41, or 47. The former are 1 and the latter 2. Since the only residue is 1, we see that minus 3 is a quadratic residue modulo every prime which is a residue. Plus or minus 5. 5 is in rows 11, 19, 29, 31, and 41 but not in rows 3, 7, 13, 17, 23, 37, 43, or 47. The former are plus or minus 1 and the latter are plus or minus 2. Since the only residues are plus or minus 1, we see that 5 is a quadratic residue modulo every prime which is a residue. Minus 5 is in rows 3, 7, 23, 29, 41, 43, and 47 but not in rows 11, 13, 17, 19, 31, or 37. The former are 1, 3, 7, 9 and the latter are 11, 13, 17, 19. Gauss's version. The observations about minus 3 and plus 5 continue to hold. Minus 7 is a residue if and only if P is a residue. Minus 11 is a residue if and only if P is a residue. Plus 13 is a residue if and only if P is a residue. The more complicated looking rules for the quadratic characters of plus 3 and minus 5, which depend upon congruences and respectively, are simply the ones for minus 3 and plus 5 working with the first supplement. For example, for minus 5 to be a residue, either both 5 and minus 1 have to be residues or they both have to be non-residues, i.e., P has to be plus or minus 1 and 1, which is the same thing as P1 or 9, or P has to be plus or minus 2 mod 5 and 3 mod 4, which is the same as P3 or 7. See Chinese remainder theorem. The generalization of the rules for minus 3 and plus 5 is Gauss's statement of quadratic reciprocity. These statements may be combined. Let Q asterisk equals 2Q. Then the congruence x2p is solvable if and only if x2q asterisk is. Table of quadratic character of primes. Legendre's version. Another way to organize the data is to see which primes are residues mod which other primes. As illustrated in the above table, the entry in row P column Q is R if Q is a quadratic residue. If it is a non-residue, the entry is N. If the row, or the column, or both, are 1, the entry is blue or green. If both row and column are 3, it is yellow or orange. The blue and green entries are symmetric around the diagonal. The entry for row P column Q is R if and only if the entry at row Q column P is R. The yellow and orange ones, on the other hand, are antisymmetric. The entry for row P column Q is R if and only if the entry at row Q column P is N. This observation is Legendre's statement of quadratic reciprocity. It is a simple exercise to prove that Legendre's and Gauss's statements are equivalent. It requires no more than the first supplement and the facts about multiplying residues and non-residues. Connection with cyclotomy. The early proofs of quadratic reciprocity are relatively unilluminating. The situation changed when Gauss used Gauss sums to show that quadratic fields are subfields of cyclotomic fields, and implicitly deduced quadratic reciprocity from a reciprocity theorem for cyclotomic fields. His proof was cast in modern form by later algebraic number theorists. This proof served as a template for class field theory, which can be viewed as a vast generalization of quadratic reciprocity. Robert Langlands formulated the Langlands program, which gives a conjectural vast generalization of class field theory. He wrote, "I confess that, as a student unaware of the history of the subject and unaware of the connection with cyclotomy, I did not find the law or its so-called elementary proofs appealing. I suppose, although I would not have expressed myself in this way, that I saw it as little more than a mathematical curiosity, fit more for amateurs than for the attention of the serious mathematician that I then hoped to become. It was only in Herman Wales' book on the algebraic theory of numbers that I appreciated it as anything more. History and alternative statements. There are a number of ways to state the theorem. Keep in mind that Euler and Legendre did not have Gauss's congruence notation, nor did Gauss have the Legendre symbol. In this article, P and Q always refer to distinct positive odd primes. Fermat proved a number of theorems about expressing a prime by a quadratic form. He did not state the law of quadratic reciprocity, although the cases -1, plus or -2, and plus or -3 are easy deductions from these and other of his theorems. He also claimed to have a proof that if the prime number p ends with 7, and the prime number q ends in 3, and pq3, then Euler conjectured, and Legendre proved, that proving these and other statements of Fermat was one of the things that led mathematicians to the reciprocity theorem. Euler translated into modern notation. Euler stated, if Q1 then Q is a quadratic residue if and only if P R, where R is a quadratic residue of Q. If Q3 then Q is a quadratic residue if and only if P plus or minus B2, where B is odd and not divisible by Q. This is equivalent to quadratic reciprocity. He could not prove it, but he did prove the second supplement. Legendre and his symbol Fermat proved that if P is a prime number and A is an integer, thus, if P does not divide A, Legendre lets A and A represent positive primes 1 and B positive primes 3, and sets out a table of 8 theorems that together are equivalent to quadratic reciprocity. He says that since expressions of the form will come up so often, he will abbreviate them as. This is now known as the Legendre symbol, and an equivalent definition is used today. For all integers or in all odd primes P. Legendre's version of quadratic reciprocity, he notes that these can be combined. A number of proofs, especially those based on Gauss's lemma, explicitly calculate this formula. The supplementary laws using Legendre symbols. Legendre's attempt to prove reciprocity is based on a theorem of his. E.g., theorem I is handled by letting A1 and B3 be primes and assuming that an contrary the theorem, that then has a solution, and take incongruences leads to a contradiction. This technique doesn't work for theorem 8. Let B be 3, and assume then if there is another prime P1 such that the solvability of leads to a contradiction. But Legendre was unable to prove there has to be such a prime P. He was later able to show that all that is required is Legendre's lemma, but he couldn't prove that either. Hilbert's symbol discusses how techniques based on the existence of solutions to can be made to work. Gauss first proves the supplementary laws. He sets the basis for induction by proving the theorem for plus or minus 3 and plus or minus 5, noting that it is easier to state for minus 3 and plus 5 than it is for plus 3 or minus 5. He states the general theorem in the form, if P is a prime of the form 4n plus 1 then P, but if P is of the form 4n plus 3 then minus P, is a quadratic residue of every prime, which, with a positive sign, is a residue of P. In the next sentence, he christens it the fundamental theorem. introducing the notation ARB to mean A is a quadratic residue, and letting A, etc. represent positive primes 1 and B, etc. positive primes 3, he breaks it out into the same 8 cases as Legendre. In the next article he generalizes this to what are basically the rules for the Jacobi symbol, letting A, etc. represent any positive numbers 1 and B, etc. positive numbers 3. All of these cases take the form, if a prime is a residue, then the composite is a residue or non-residue, depending on the congruences. He proves that these follow from cases 1, 8. Gauss needed, and was able to prove, a lemma similar to the one Legendre needed. The proof of quadratic reciprocity is by complete induction for each of the cases 1 to 8. Gauss's version in Legendre symbols. These can be combined. A number of proofs of the theorem, especially those based on Gauss sums, or the splitting of primes in algebraic number fields, derive this formula. Other statements note that the statements in this section are equivalent to quadratic reciprocity. If, for example, Euler's version is assumed, the Legendre-Gauss version can be deduced from it, and vice versa. Euler. This form of quadratic reciprocity is derived from Euler's work. Euler's statement can be proved by using Gauss's lemma. Gauss's fourth proof consists of proving this theorem and then restricting it to 2 primes. Let A, B, C be unequal positive odd primes, whose product is n, and let m be the number of them that are 3. Check whether n, A is a residue of A, whether n, B is a residue of B. The number of non-residues found will be even when m 0, 1, and it will be odd if m 2, 3. He gives the example. Let A equals 3, B equals 5, C equals 7, and D equals 11. 3 of these, 3, 7, and 11 3, so m3. 5 times 7 times 11 are 3, 3 times 7 times 11 are 5, 3 times 5 times 11 are 7, and 3 times 5 times 7 and 11, so there are an odd number of non-residues. Eisenstein formulates this. Mordell proved the following to be equivalent to quadratic reciprocity. Jacobi symbol. The Jacobi symbol is a generalization of the Legendre symbol. The main difference is that the bottom number has to be positive and odd, but does not have to be prime. If it is prime, the two symbols agree. It obeys the same rules of manipulation as the Legendre symbol, in particular, and if both numbers are positive and odd. However, if the Jacobi symbol is +1 and the bottom number is composite, it does not necessarily mean that the top number is a quadratic residue of the bottom one. Gauss's cases 9, 14 above can be expressed in terms of Jacobi symbols, and since P is prime, the left-hand side is a Legendre symbol, and we know whether M is a residue or not. The formulas listed in the preceding section are true for Jacobi symbols as long as the symbols are defined. Euler's formula may be written, for example, and 2 is a residue mod the primes 7, 23 and 31. 32 2, 52 2, and 82 2, but 2 is not a quadratic residue, so it can't be 1. This is related to the problem Legendre had. If we know that A is a non-residue modulo every prime in the arithmetic series m plus 4a, m plus 8a. If there are any primes in this series, but that wasn't proved until decades after Legendre. Eisenstein's formula requires relative primality conditions. Hilbert symbol. The quadratic reciprocity law can be formulated in terms of the Hilbert symbol, where A and B are any two non-zero rational numbers and V runs over all the non-trivial absolute values of the rationals. The Hilbert symbol is 1 or -1. It is defined to be 1 if and only if the equation has a solution in the completion of the rationals at V other than. The Hilbert reciprocity law states that, for fixed A and B and varying V, is 1 for all but finitely many V, and the product of overall V is 1. The proof of Hilbert reciprocity reduces to checking a few special cases. and the non-trivial cases turn out to be equivalent to the main law and the two supplementary laws of quadratic reciprocity for the Legendre symbol. There is no kind of reciprocity in the Hilbert reciprocity law. Its name simply indicates the historical source of the result in quadratic reciprocity. Unlike quadratic reciprocity, which requires sign conditions and a special treatment of the prime 2, the Hilbert reciprocity law treats all absolute values of the rationals on an equal footing. Therefore it is a more natural way of expressing quadratic reciprocity with a view towards generalization. The Hilbert reciprocity law extends with very few changes to all global fields, and this extension can rightly be considered a generalization of quadratic reciprocity to all global fields. Other rings. There are also quadratic reciprocity laws in rings other than the integers. Gaussian integers. In his second monograph on quartic reciprocity, Gauss stated quadratic reciprocity for the ring Zi of Gaussian integers, saying that it is a corollary of the biquadratic law in Zi, but did not provide a proof of either theorem. Peter Gustav Legendre showed that the law in Zi can be deduced from the law for Z without using biquadratic reciprocity. For an odd Gaussian prime pi and a Gaussian integer alpha, GCD equals 1. Define the quadratic character for Zi by the formula let lambda equals a plus bi and mu equals c plus di be distinct Gaussian primes where h and c are odd and b and d are even. Then where is the Jacobi symbol for Z? Eisenstein integers. The ring of Eisenstein integers is Z omega, where is a cube root of 1. For an Eisenstein prime pi, n pi 3 and an Eisenstein integer alpha, GCD equals 1. Define the quadratic character for Z omega by the formula let lambda equals a plus b omega and mu equals c plus d omega be distinct Eisenstein primes where h and c are not divisible by 3 and b and d are divisible by 3. Eisenstein proved. Where is the Jacobi symbol for Z? Imaginary quadratic fields. The laws in Zi and Z omega are special cases of more general laws that hold for the ring of integers in any imaginary quadratic number field. Let K be an imaginary quadratic number field with ring of integers for a prime ideal with odd norm, and define the quadratic character for by the formula for an arbitrary ideal factored into prime ideals. Define and for define let be an integral basis of for with odd norm nu. Define integers a, b, c, d by the equations, and define a function chi where nu has odd norm by if m equals n mu and n equals n nu are both odd. Herglotz proved also, if polynomials over a finite field let F be a finite field with Q equals Pn elements, where P is an odd prime number and N is positive, and let Fx be the ring of polynomials in one variable with coefficients in F. If an F is irreducible, monarch, and has positive degree, define the quadratic character for Fx in the usual manner.